All right, so thanks for sticking around at the end. Hopefully this is interesting. So I'm talking about my oven. As a quick reference, these slides are up on my website, which will be at the end, but colino'flynn.com as well. So this talk came about because I have the oven on the left there, and I had some issues with the oven. And the issues with the oven came out because of, in Canada, we have Thanksgiving before the American Thanksgiving. So yes, woo, indeed. Early October-ish. And normally you cook a turkey for Thanksgiving, but the past couple of years we'd been doing a ham instead. The reason being that our oven had this weird thing where it seemed like it was not heating correctly and things were taking too long to cook. And we had some very unruly sort of people living with us that really wanted their dinner on time. So when dinner was delayed, they were less happy. And I didn't really think much of it until I had seen a news article about a different Halifax area man had an issue with his oven. In his case, his caught fire, so that seems somewhat worse. But basically, in this article, they mentioned that this guy had this problem with his oven. It was overheating. And they mentioned that actually there's some class action lawsuit against this oven, including my oven. And there's a whole bunch of complaints, mostly around temperature regulation. So it might not actually be just my oven that's defective. It might be a whole class of them. And they had some vague claims like, the sensor, something like that. But I suspected there was more to it. So this kind of set me on a path to figure out what was wrong and if I could actually fix it. So just really briefly, if you take your oven and look inside it, you'll see something like this. So there's a control board in the middle there. So this control board is controlling the heating elements right in the bottom part here. And this is all the brains of the oven, more or less, right? So if you take that control board, I went on eBay and got one that I thought was more or less compatible. It looks something like this. And on the backside, there's a single chip. So this microcontroller here is running all of your oven control logic. So this logic is everything that's trying to regulate the temperature and stuff like that. So this is, the magic of your oven is in that microcontroller. If there's problems with the software, they're also in that microcontroller. And so my suspicion about this whole, thing is that actually maybe it's a firmware issue. And the reason I suspected that is that if we would see our oven just displays the temperature it's set to, and if you stop the oven and restart it, it'll show the temperature it knows it is, and it's much lower. So something was weird, right? Like it knew the temperature was wrong, but it wasn't fixing it. So the goal of this talk was to figure out what's going on and then figure out if I could fix it. So inside the oven, it uses this old TMP91 FW60 microcontroller. So this is an old microcontroller from Toshiba. It's this TLCS 900L1 kind of series CPU. So it's the 16-bit CPU. There's a few variants of it, or a few different versions that have very similar names but are quite different. So they have the H, which is a 32-bit, and that one's used in some other stuff that has a lot more reverse engineering work. This one it seems to be used or known less frequently, so there's less information available on it. The important thing, though, so what I wanted to do, number one, get the binary out of it. Number two, reverse engineer it. Number three, see if there's a problem, and then maybe fix it. So I needed to be able to read that out as well as program it. The device has, there's no programming tools I could find, but the datasheet describes in detail the bootloader, and so the bootloader has a few commands. It has a RAM transfer, so this is for a second stage bootloader. It has a checksum command, flash memory sum. You can read product information, including security features that are enabled. You can erase the device, and then you can set. The final one is setting a protection mode. You notice there's no like flash read or flash write, so you need a second stage bootloader for this to work. For the second stage bootloader, this command in particular has an option to enable, basically there's this protection applied error it describes, which if you try to do it, it's going to first error out if someone's turned on protection mode, and if that passes, it's then going to ask for a password. So there's actually two levels of security that you can enable. The other command of interest of setting the security mode to turn that on, it requires only the password. And the reason I single these two out is basically there's two different security levels that can be enabled, the protection flag as well as a password. And we also have functions that use only one of them or use both of them. So this is really handy when we go to do our attack in a second. Before I do that, I did need like a programmer, a simulator, emulator, all this stuff to be able to actually use it. As I said, I couldn't find a lot of it. Luckily, there was some old dev kits, so it wasn't this much, but you can find them on eBay and stuff like that. So I was able to get the dev kit, and there's a really nice, runs in Windows XP sort of simulator, as well as an assembler, disassembler, all that stuff. So I mirrored it here, so all these links are on the slides at the end too. If you are running into this device by chance, because it is actually quite nice. You can also read back the bootloader, so you can get all the bootloader binary out, which is good because we want to understand that bootloader to bypass the security features. Okay, so this is reading back the bootloader. Two kind of important things I want to highlight, because then I'm going to show how you can bypass them. This is part of what's getting the password. So it's receiving the password and then verifying it. There's kind of this loop here, jumping up to E2. So this is the important part, where it receives a byte of the password, right? So it receives it here, it compares it, and then if the comparison is fine, it skips over setting this flag. So there's this one flag that gets set if the password's wrong. So that's kind of one thing there. So the difference here is that we have some control flow that changes depending if the password is right or wrong. So this often means there's some sort of side channel that we exploit. The other function of interest is the function that actually, and so this function, by the way, you can see it doesn't check the protect flag, it's just looking at the password. The higher level one, which is the function that takes that second stage bootloader, you can see all it does is it just has a compare for this protection status. So basically what we're going to have to do is we're going to have to bypass that line to be able to skip all the protection checks. So basically there's two things that are that point to the attack method. The password check having this code flow dependency, and the fuse byte having this one line of code that if we skip that line, everything's fine. So if you deleted this line, then it's never going to do anything, or you deleted really like the jump right to the fail. So we're going to start doing this the easy way and then apply it on the real oven board. So the easy way is something called project started a long time ago, ChipWhisperer, which now has various updates to it. So this hardware on the left, ChipWhisperer Husky, JP and Alex, who were sitting over there, they helped develop a lot of this. JP did all the FPGA, which is open source. You can run it on a simulator too, so it's really cool. You can add all sorts of stuff, like triggering on ARM trace packets, triggering on UART, triggering on power traces. So there's a lot of cool stuff baked into it. So what I did is I built a board here that uses a similar chip to in my oven. I couldn't find the exact same one, but I could find a bunch of a very similar chip on eBay to build this board. So what I'm going to do is I'm going to attack the bootloader using that chip and then apply it to the real oven board with the chip here. So the first thing we can do is look at power analysis. So if you don't know power analysis, really briefly, how it works is we get a microcontroller. So this thing right here is this block here. I have control over the microcontroller. I'm going to send it, for example, a password. While it's processing that password, I measure with very high precision the power used by it. And I measure the power with a physical, so there's some connections on this board that basically go here to this cable, and then this cable goes here. And so it's just measuring, it's custom designed to actually do that measurement, and it's very low noise and stuff like that. So you can do it other ways too, but in this case, it's easy mode. I've made a board that does it, and it works really well. So to show you what that looks like, I have, if I scroll up, so this stuff, Jupyter Notebooks, if you haven't seen them, it's all just Python code running. So basically, I have the board plugged in up here, and what I'm going to do is program it with, so I erase the device, and then I'm going to program it with this password, right? So I start with 5 because I want to do a short number of guesses, so I use the low value here. So there's a 12-byte password I just programmed in, and there's some code that's just resynchronizing, so nothing too important. The important thing is here, what I'm going to do is I'm going to write like several different password guesses. I'm only doing like, sending hex 0, hex 1, hex 2, etc. To it. and then at the same time, I'm going to plot the power used by the device as it's processing this. So what you kind of see is that at some point, if I start here, there's sort of 10 different power traces overlaid. Each of these corresponds to the device as it's processing a different value of the password. And you can see they're all aligned, because what's happening here is at this point in time, the device is in this early part of the code where there's no data dependency. So like up until this point, it doesn't matter what the password is. It's always taking the same code flow. After that point in time, there's that jump that'll happen, and that jump happens every time the password's wrong, and it won't happen when the password's right, or the character of the password. And if we scroll over, and sorry, the zoom's weird because of the browser, you can see there's this one point in time where there's one different power trace. So this is how we do kind of power analysis. We detect this difference, and then we know, this is the case where the code did not go into that jump, or it did not set the fail byte. So in this case, it accepted that byte of the password. I then just basically continue the attack by knowing the first byte, then break the second byte, third byte, fourth byte. So it's quite quick in that way. And because this password is shared, I really only have to do it once. So there's an example, right, with just 4, but it's the same thing. So you're seeing there's some difference for the right value. You can plot it. So in this case, what I did is I just plot an average value and then find the one outlier, and that's the correct value of the password. So that we'll bypass the password. The other thing we have to do is fault injection. So we need to kind of delete, I had said that this one instruction here, this thing that's jumping to, right, sending the error if the protection's enabled. If we skip that, it's just going to go right to the password check. So that's what we want to get to. So we use fault injection to do that. Very briefly, fault injection works in the idea that if you have a microcontroller, normally they have some pipeline that's executing all your instructions. A really simple pipeline might fetch from flash the instructions. It's decoding that instruction at the same time it's fetching the next one. After it's decoded, in this case the compare, it'll execute it. Execute means writing all that stuff back, so like setting the flag values and stuff like that. We can have more stages in the pipeline, of course, but for our purposes, this is good enough. So the point is we have this kind of complex system that's working on different parts of the program in different ways. And again, that's just continuing. When that's actually implemented, we implement it as like typically registers. So this is simply a register or flip-flop. And the way this is done is you have a clock network, and this clock network is distributing a clock to all of these flip-flops or at the same time. And in between the flip-flops, I have this logic here. So we have our clock that should be very regular, right? And this logic in between it is quite a bit slower. This logic would be doing this stuff like some of the decode or some of the execute or whatever it is. The logic is going to depend on obviously the stage, the breakdown. Like this could get broken down into more than just a couple flip-flops. But the point is that because this logic is much slower than the clock network, if the data that's going through this logic takes longer, this combinational logic takes longer than the clock period, right? It's not going to reach the input in time. So it needs to go from the output of one flip-flop to the input of the other in between this time window. And this kind of defines, how fast the processor can run and stuff like that. We can basically cause a fault because if it doesn't reach it, right? If it reached it over here, if I delete this dot, you get the idea, right? If it reaches it too late, then it's registering the wrong data. What does that mean? That means that, for example, it never actually decoded the jump instruction because it didn't have time, because it didn't process through the logic. And basically the two ways that we do that is we either insert an additional clock, which causes, that's just too fast, or we slow down this logic by very carefully lowering the voltage at a very specific instance in time, and the lower voltage causes a longer logic propagation time, which also gives us a fault. So that's two different ways of injecting it. In this case, this older device directly uses the clock. So I can use clock glitching and basically just insert into the clock an extra little pulse. And the trick is I need to find the settings for where the clock goes and how wide it should be and stuff like that. Because remember, this clock goes to the whole chip. I don't want to necessarily mess up all of the logic. I just want to mess up part of the pipeline stage. And what I'm trying to do is find perfect settings that it's fast enough that some of the other logic is still working. It accepted the faster speed, but part of the pipeline maybe that's processing that instruction falls down and doesn't process the instruction, and I get a successful fault. So we need to do this tuning aspect. The other part of this is that on this device, it also had this really nice checksum instruction. So we had a checksum instruction. We can send it to the device checksums the flash and returns the value of the checksum. This is really nice because at this point in time, it's going to take a while. I can try inserting glitches and basically see if I can impact that without crashing the device. I still want it to operate correctly after, because in real life, I need to skip that one instruction, and then the rest of the program has to run correctly. So that's basically what we try to do, is we then try to just sweep through a whole bunch of settings for this device. So what I do here is first I'm sending it the checksum request, and whatever response it gives me, I just use as kind of a, okay, this is what I expect. If I get something different, I should consider that successful. So this stage would take a while. In reality, I'm not going to run the full thing. But if we scroll up here, you can see this normal count increasing slowly. So every time it's just doing a checksum request. At the same time, it's then seeing, hey, did I get a faulty value back? If I get a faulty value back, it calls it a success. So we see one little point here. And all I'm trying to do is find some settings that could be interesting. So if we let that run a while, what I would hopefully see is something like this. So this is showing after I ran, there's all these areas that are showing interesting areas where I'm getting faulty results. So if I take these settings, I can then apply them to what I really want to do, which is bypass that read protection check. So that's the real goal of it. So to complete the attack, let's see if so I got 3 here. So you can see how there was like 100 little before, but I'm just going to take one of these. Oops, come on. I'm going to take one of these green sort of spots, and I'm going to record like a width of 100 and offset of 400. This is just some settings for the glitch. And then what I'm going to do is I'm going to, and I already forgot them, width of 100, offset of 400. I'm then going to use those and then basically have the device request that it does a second stage bootloader. And so I'll pop them in wherever they are down here. 100 and 400. So I think it was a width offset of 100, a width of 400, I said. And this one, again, may or may not work. But basically, I just asked the device to do a second stage bootloader request. And if you get lucky, this one will take a while. So what you want to see typically with glitching is that you're getting some resets. So if I go up and look at my thing, I see a lot of normal counts, which could be okay, but I should be right on the edge of it being stable. So what you hope to see is you also get some resets or something in there. So I may have had to let it run longer before I get that. But eventually it's going to bypass that the write protect flag, and then I can continue with the second stage bootloader and read out the memory. So that's the idea. So this was just on my little target board here, but it gave us, a Python class for communicating with the device. It gave us timing on power analysis, and it gave us timing on fault injection. So now what we do is we do it in a slightly more difficult mode, not even that difficult, where we take the physical oven board, or the one I got on eBay, so this wasn't from my oven yet, and we try to do the attack. So it's pretty easy on this board because there's like a really nice spot that you can cut a jumper and put a resistor in for doing power analysis. There was a crystal here that I removed, and I added wires to do the clock glitching, so it's a pretty straightforward type of attack. And we do power analysis exact same way I just showed you, except now we're going to recover the real password. So for dramatic effect, I just made it spell it out. But it does it one character at a time. So it gets one character, I feed that in, so it can then break the second character, and then it gets the next character. So, so with this password, I can then try to do glitching on it. So Samsung oven 0. So yeah, so that will allow you to flash these ovens. So the second part is, now that I know the password, right? So this was the whole thing. I needed the password because if my fault injection is successful, it'll require the password for me to continue. So I tried it. It was successful. I then put that in, read out the data. When I read out the data, I got all FFs. So this wasn't good. Did something mess up? And then when I checked, because I can do that product info, which is telling me if it's protected or not, and it says it's not. So what actually happened here is, if you look at the bootloader code, there's also, it's jumping to the bootloader command, and I accidentally glitched it, so it jumped to the erase command, and when it jumped to the erase command, it erases itself and comes back that, oh, it's unprotected. So I thought the attack worked. So that wasn't very happy. I didn't want to wait on eBay, so I went to a repair store locally and bought a brand new one of these boards. And when I was setting it up, right away it said read not protected, write not protected. So what I think they actually had issues, I'm guessing, with returns, and because they had enabled the protection, they couldn't check if Flash was getting corrupted or something. So this means you only need the password. I don't actually need to do the fault injection part of it at all. So that was cool, but it's also like kind of disappointing because that was fun. So then you get the firmware out of it. Okay, very good. As a quick side note too, I did try as a proof of concept, so this little Pico EMP device I made. So this was a cheaper way of doing it, right? So this is a Raspberry Pi Pico that's doing the that protocol I talked about, and it's triggering EMFI. So EMFI is another way of doing fault injection. We basically use a strong magnetic field, introduces changes in the voltage on the chip, which causes those time delays, which then causes faults. So I tested this on the checksum, and that successfully worked. I didn't test it on the full password, like second stage bootloader, because it turned out not to actually be needed most of the time. All right, so now we have the binary. You probably expect the next slide's talking a lot about reverse engineering tools. What does it use? Well, screw those. We're going to use Excel because the software outputs a nice text file that had all this data, and I just tabbed, eliminate, import to Excel, and make my little notes. And you know what? It works, so too bad. The devices actually have some sort of serial monitor in them, so I figured out you can send a command to it, and it returns with some flags. It's not documented, so that could actually be useful for repair. But I also could modify it to make a memory dump monitor, right? So that was one of the goals, is I want to dump the memory as it's running so I can figure out what it thinks the temperature settings are, so I can figure out what's going on with the control logic. So we take that board, we put the board in my oven, and the oven says E84. And it turns out I got this board, the F, and I needed this board, the D. So I couldn't use the board off eBay or the second one I bought from the parts department. But I do have a board in the oven, obviously, that's working. And so we take the oven PCB, we put it on the bench. It still had the protection. It's an older board. The older boards have the protection. And then we also get FFs, and we erase it. So I also, at this point, the issue was I was pretty confident it was going to work. So this was like at night, and I told my wife, it's fine, don't worry. I'm not breaking the oven. And I broke the oven, so that's in fact what happened. Anyway, so then I bought another board, the correct board, the D board. This board did not have the read protection enabled, so there's no risk of bricking it. And yeah, I was able to get the right firmware. So as a side note, that I think the issue is I also was basically when I was timing my glitch, I had this sweep that just sweeps around to figure out where it is. If you think about the logic of it, earlier on, it's going to be doing the kind of decision on where to jump, what command it's processing. So I think I just was sweeping too early on. I should have changed the logic, but then because I didn't really need to make it reliable, I didn't push that much further. So once you have that, basically you can swap between the firmware. So to program this, I have an isolated USB serial. It's just TTL serial if you want to do this. So then you can reflash your oven with the correct firmware. and then once that's done, it'll reboot and basically, hopefully the whole thing works. So this is just getting it back to functional. This is not very advanced hacking yet. Yeah, so there you go. So it's a working oven, great. The interesting thing too is that I could see, so before I erased my board, I did check the checksums, because that's a command you don't need the password for, or anything for really. And the checksums differ, so there could have actually been firmware fixes. There's of course no firmware update instructions. The Samsung is just buy a new board if you want a firmware update type thing. So the other point of this talk was a lot around, e-waste reduction and repair, because, these boards don't do any check on boot if there's like a flash errors or something. So this is one of the interesting things, is it seems like there could have been, I don't know if it's constant changes. It seems like it wasn't. It was firmware changes, but you can now use these to just reflash a board instead of replacing it. So into that firmware, the revision D that I had did not have the serial monitor. So basically using my Excel reverse engineering / assembler, I inserted the serial monitor code into my oven version. Minor risk here is I kind of stole some addresses for global variables, and I don't know, hope it doesn't hurt anything. There's an extended slides where I detail, the process of actually finding all of the interesting variables, but basically you can find the variables. So you can find, for example, what the temperature is in Fahrenheit. If anyone's from Europe that doesn't know, so in Canada we use Fahrenheit for ovens and pool thermometers, but Celsius for like general temperatures, so that's just normal. Anyway, and there's flags that tell you if like the heater is on or not. So yeah, so you can get all this information out. So now the important thing is finally I can do a test to see what the oven thinks its temperature is. So I take a shepherd's pie, put it in the oven, turn it on, or actually no, I don't put it in yet. That's a lie. I turn on the oven, and you see the oven heats up. At this point in time, the oven starts displaying 375 as a temperature. So it stops telling me the real temperature. It just always displays 375. At this point here, I open the oven, put the shepherd's pie in, and what you can see is the temperature drops and never recovers. All these little negative spikes here, when the heater turns on, the temperature drops. The measured temperature drops because of electrical interference. So you can see that it's just doing this pulsed heater on pattern. So it's actually not strong enough to recover the temperature. So this was actually the problem that I was seeing with my oven, is related to either the heating coil, I suspect maybe has aged, isn't as effective, and their control algorithm doesn't have the ability to counteract that. So the first thing I did is I patched the display logic to always show the actual temperature. So normally it won't show you a temperature below 150 Fahrenheit, so here you can see it doing that. The second thing I did is I patched the cooking logic to basically keep it in that first more aggressive temperature mode. And I also fixed the display by adding, like when the heater's on, it adds this offset to the display that more or less fixes it. So with this, when I put my thing in the oven, and I open the oven right here, you can see it dropping. You can see this is actually maintaining a lot closer to the 375 it should. The other thing I did, so if you watch like baking shows, they often use a souffle, because in theory, so I don't know, this is the first time I cooked a souffle, but I've heard that they're very sensitive to temperature drops, and so you can use this as a reference for an oven. So yeah, it looks very pretty. I didn't have any of that stuff, so I used a little square thing, and I'm told this should work, according to the internet. And sorry, and then I had the rack on the wrong level, so the video is less exciting because of that. Anyway, but yeah, so you put the souffle in the oven, and then the question is basically, are those, because you can see there's larger swings, because now it's much more aggressive with the temperature. It's working actually more like a mechanical thermostat than it was before, where they had this weird control algorithm. And you can see here it's displaying the actual temperature that's going up and down, which it wouldn't do normally. So when it came out, it looked pretty good. It rose a bit, it tasted fine. So as far as I'm aware, that's a souffle, and there's a recipe if you'd like to try. Recommend it. There's some bugs with this patch that I haven't fixed yet. So after a length of time, so after it's been running for so long, it kind of stops working. So it won't heat. You have to power cycle it at the breakers. And I don't feel bad about this, because like the Patriot missiles had this issue. So you know what? I don't feel bad. So that's still to do. And this might be the monitor I added because I just took some global variable addresses and used them. So I don't know if I like overwrote something eventually. The other thing, so if you want to do this, there's at least two, there's probably more main versions of the board. So if your board doesn't have all the stuff on top and says FM new main, it has a totally different microcontroller, which is actually supported in Ghidra, and you can read it out with a debugger. So it doesn't need as much crazy stuff, but I haven't actually gotten to the point where I've patched it fully. But this same oven with the same board, actually my parents have this same oven, and they were the ones that were also complaining about it. So it's a totally different board, totally different architecture. I suspect it's the same sort of software issue. If you want to do it, be aware that there's some increasing levels of danger. And the reason I point this out is that, okay, so the top range part, they have knobs. You physically turn on the knobs. The heating elements in the oven are all under firmware control. So there's buttons, yes, but they're just software buttons. So, you know, when you're thinking about this, just be aware that you're patching this and it can just turn on, in theory. Right, if it's wrong. So yeah, so that's kind of where I end up. So really the point of this was that, you know, it might not be fault. So if you have one of these Samsung ovens and you've been struggling, it's probably not your fault. A lot of them do this though, they kind of lie to you. They only show the set temperature or some, you know, fake temperature. And I think it's to hide some of these weird issues with, you know, oh, the temperature drops when the heater turns on, stuff like that. The bigger problem, right, is there's so much wasted e-waste, like at least parts for sure, but I'm sure people have replaced their full oven. So one of the goals of this was to see, can we release tools, can we release information that helps people fix these? Because as far as I can tell, the hardware is totally fine. It can be repaired in software. And even just reflashing the boards, right, could be a regular repair item, even though right now it's not. And the other thing is too, of course, that these chips are EOL. So I don't even know if Samsung is going to continue making control boards for this oven, right? So people might be trying to replace the control boards and not even able to. So that's the other thing, right? Is that being able to reflash it's really important for that. So if you're interested, as I said, these slides I put up online. There's a GitHub repo with some of the technical information. There's some resources, and the examples I ran on the glitching and power analysis are also on that repository there. With that, if there are questions, otherwise you can talk to me later. If you just want to leave, I won't be offended.
With all the work and the time you put into getting all the information about the oven and the controls and everything else like that, did the food at least taste good at the end?
Yeah, well, yeah, so it did, and before it kind of worked, but it did taste good. The souffle was good, the shepherd's pie was good, so if nothing else. Any other questions over here?
So with all that new knowledge about like oven, any plans to make a kitchen-sized reflow oven with all your new ideas?
Yeah, this is a good question, actually. You could, with this, you could reflash it to make a reflow oven out of your kitchen, or a board drying oven or something, right? You can do anything. I didn't think of that, actually.
It's like the Contraleo 3 something, like you can buy a kit to turn your toaster into a reflow oven, so maybe a kitchen-sized one.
That'd be pretty cool.
Can you give us any social engineering tips for convincing your partner in terms of, can I play with the one oven in the house that I might accidentally set on fire?
So she actually had noticed this problem too, and so she was pretty supportive of it because it was a question of like, I forget what she was making, because so the other people have realized that this is a problem, and you basically restart your oven, so you stop it and restart it mid-cooking, and then it'll show the new temperature, and it looks like it's recovered. But they actually make it worse because of the way they lie about, so when it turns on, it always over peaks, but it stops displaying this higher peak. So I think she was burning cookies or something, and she's like, I don't understand what I'm doing wrong. And it's like, no, actually, it's just the oven stopped showing that it's doing this crazy thing. So that was good. Yeah, if it was a fully functional, I probably would have had less support, I imagine. Right, I don't see, yeah, anyway, as I say, if you have questions, come up to me later. I know it's end of the day. I don't see any other hands, so with that. on hand. And in the meantime, there is the party at, what time is it again? 8:30? Boom, there you go. Doors open at 8, do not be late.
Why Excel?
Why Excel? Because I couldn't understand how, and maybe can someone tell me if this is possible? So basically, I tried using some plugins I found. They didn't work very well for this specific device, and I had this really nice disassembler that just generated a big text file. So yeah, I assume there must be some way that you can feed that information into something smarter, but I was not the smarter person there, so. And it actually works pretty well because you can like find on addresses, on instructions, and it gives you all the hits in a big list. So it was actually better than I thought. All right, thanks everyone.